In this video I'm going to talk about electromagnetic induction, which is a key concept in this topic. So what we have here is we have a bar magnet, and we have a coil of wire connected in series with a resistor, and across the resistor we have a voltmeter which can measure both positive and negative voltages. Now you see the bar magnet is stationary, as there's no movement, so there's no change in magnetic field, and therefore there's no voltage or induced EMF. But as soon as I move the magnet, you see there's a change on the voltmeter, and you can also see that within the coil there's a movement of electrons, so therefore, since there's a flow of electrons, there's also a current. Now if I move the magnet faster, you should see that there was a larger movement on the voltmeter. So it has to do with something to do with the rate of change of magnetic field. When there's no change in magnetic field, there's no induced EMF. But as the magnetic field changes within the area of the coil, there's an induced EMF, and this this flow of current, this induced current, and therefore induced EMF, is what we call electromagnetic induction. And if I increase the number of loops to 3 and try and move it at the same speed, kind of hard to show it here, but the more loops I have, the greater the induced EMF I have. The weaker the magnetic, if I put my magnetic field strength down to 0 there, there's going to be no induced EMF. But if I only have a weak magnetic field, there's going to be a smaller induced EMF. So again, a uniform magnetic field within the coils has no induced EMF, but as soon as there's a movement of the bar magnet, there's a change of the magnetic field, therefore there's an induced EMF. And as the north pole approaches the coil this way, I get a positive voltage, positive EMF. As it leaves, then the polarity changes, I get a negative EMF.